Hey there and welcome to this explainer. Before we even dive in, I want you to just take a deep breath, drop your shoulders, and relax for a second. Chances are you're an engineering student, or maybe you're just someone trying to navigate the notoriously dense, sometimes totally unforgiving world of electrical circuits. Well, you're in a safe space here. Today, we aren't going to drill you with endless equations, and we're definitely not testing your memorization skills. Instead, we're going to look at a fundamental concept that's actually designed to make your life drastically easier. We are going to explore the beautiful, almost magical concept of the equivalent circuit. So let's just find some peace in the circuit together.
It's honestly a universal experience, right? You're sitting there at your desk, it's way past midnight, the glow of your lamp is basically the only light in the room, and you turn the page of your engineering textbook. And suddenly, you're confronted with a schematic that looks way less like a learning tool and more like this tangled web of lines, symbols, and mathematical jargon. You feel that sudden spike in your heart rate, your chest tightens up. That overwhelmed feeling, it is incredibly real. And if you've ever felt that way, I really want to validate that for you right now. The way these concepts are traditionally presented can be so intense, but today we're going to completely shift that perspective.
I mean, take a look at this. This is what you usually face out in the wild. You've got handwritten Kirchhoff's voltage law, loop analysis, simultaneous equations, sprawling matrices. It is just so much visual noise. Just looking at these three interconnected loops with multiple resistors and voltage drops being calculated simultaneously, it's really no wonder you feel anxious. We've got I1, I2, fractions, determinants. It looks like a mountain you have to climb with your bare hands. But I want you to recognize something absolutely crucial here. Much of this is literally just an illusion of complexity. All of this math is simply describing a physical reality that at its core just wants to reach an equilibrium. And here's the secret. Our main goal today is to strip all of that noise away.
Okay, let's dive into this, but seriously, without the stress. Here is another classic source of late-night panic: nodal admittance matrices. You see nodes, conductances, current sources, and a symmetric matrix forming a massive system of equations. Your brain is trying to process G1, G2, V1, V2, all at the exact same time. It is a perfect recipe for cognitive overload. When you look at a circuit like the one at the top here, your instinct, which has been trained by years of schooling, is to try and solve the entire thing at once. You want to understand every single current in every single branch simultaneously. But what if I told you that you almost never actually need to do that? What if there's a way to cheat the system perfectly legally and just bypass that overload entirely?
To wrap our heads around how we actually do that, let's just step away from the textbook for a second. Imagine you buy a brand new desk lamp and you want to turn it on to study. Do you sit down and calculate the current flowing from the massive power plant 50 miles away? Do you model the resistance of miles of high-voltage transmission lines, the step-down transformers in your neighborhood, and all the intricate wiring hidden inside your apartment building? No way. Of course not. That would be absurd. Literally all you care about is the wall outlet. As long as that outlet provides a simple, reliable 120 volts, you do not care what the rest of the city's power grid is doing. The wall outlet is essentially just a simplified stand-in for the entire complex system behind it.
And honestly, that brilliant little realization brings us right to our core concept, the equivalent circuit. By definition, an equivalent circuit is simply a way of replacing a complex mess of components with a simple substitute that acts exactly the same way from the outside. I really don't want you to frame this in your mind as just another punishing set of math rules you have to memorize for some midterm. Instead, I want you to view it as a philosophical tool. It's a mental black box. It's an acknowledgement by engineers that life is just too short and our brains are way too valuable to calculate every single node every single time. It's a strategy completely designed to make your life, and engineering as a whole, drastically easier.
Now, what's really interesting here is how this visually proves the magic trick. On the top, you see a box labeled N1, and it's connected to a box labeled N2 at two terminals, A and B. Just imagine N1 is that terrifying, messy circuit from our earlier diagrams, the one with all the loops and matrices. Now look right below it. Through the magic of what we call a Thevenin equivalent, that entire terrifying N1 box has been completely erased. It's been swapped out for just two simple things: a single voltage source called VOC and a single resistor called R0. From the perspective of the load, which is N2, absolutely nothing has changed. It still receives the exact same voltage and current. The complex city grid has basically just become your simple wall outlet.
So the absolutely crucial thing to grasp here is what's actually going on inside that black box. All that internal chaos, the sprawling matrices, the complex KVL loops,
those messy fractions we saw earlier, well, it's all still technically there, sure, but it is entirely hidden inside the box. As an engineer trying to power a specific load at the output, you simply do not need to care about the internal politics of the circuit. We only care about those two output terminals, A and B. We are actively making the choice to ignore the internal workings because, at the end of the day, they don't matter to our final result. We're protecting our energy and our focus by isolating the system.
So let's move to how we actually do this and see how it builds our understanding without relying on any punishing math. Finding this equivalent circuit is actually a surprisingly low-stress three-step process. Step 1, you just remove the load. You disconnect N2 entirely. Just pull it away and look at the open terminals. Step 2, you find the open circuit voltage at those empty terminals. Imagine you're just hooking up a voltmeter straight to the wall outlet. That gives us our open circuit voltage, or VOC. And step 3, you find the internal equivalent resistance looking back into that outlet, which gives us our R0. And that is it. You analyze the problem once, package it up neatly into a simple source and a simple resistor, and you literally never have to do the messy math for that section ever again.
You know, engineering really doesn't have to be this endless exercise in suffering. It is fundamentally an exercise in problem solving, and the most elegant solutions are always the simplest ones. Remember this. Complex systems can always be simplified to their essence. You have the power to reduce overwhelming, anxiety-inducing complexity into something that is universally understandable and, a whole lot more importantly, highly manageable. The next time you're facing a dense, intimidating schematic, please don't let it spike your heart rate. Just remind yourself that there is an equivalent, simpler truth waiting to be found right inside it.
As we wrap up this explainer, I kind of want to leave you with a thought that extends a bit beyond the pages of your textbook. This whole philosophy of the equivalent circuit, of taking a sprawling, chaotic system and reducing it down to its simplest functional, outward-facing parts, it's incredibly powerful. So maybe take a step back from your studies today and just ask yourself, what complex mess in your own life could use an equivalent circuit? Where are you calculating the whole city power grid when you really only need to find the wall outlet? Thank you so much for taking this time to learn, to breathe, and to focus with me. Until next time, keep simplifying.